Hey everybody, it's Miss Smith. So today we are actually going to start Unit 3, which is waves, sound, light, all of those fun things. And so before we get into our notes today, I want to just show you a quick little clip that I will refer to throughout really the unit. That's a weird phenomenon that happened based on an engineer's mistake, several engineers' mistakes. And so this has actually happened more than once. But this is the Millennium Bridge in London, and this happened in 2000, the summer of 2000. And after this happened, they had to shut it down for 2 years to fix the bridge. And then that opened up back again in 2002. But this happened also in Tacoma, Washington. It's called the Tacoma Narrows Bridge, or Galloping Gertie, if you want to look that one up. Anyway, so I'm going to show you this clip and I'm going to kind of talk about it a little bit. Let me make sure the sound is off. I don't know where it is. Okay. So if you watch, the people are swaying back and forth. So the bridge is actually swaying back and forth. And so this bridge got the nickname Wobbly Bridge. And so this is it's a famous bridge. You can see it in water movies, but it's famous because this is what happened. And so what happened are the engineers didn't take into account when people would get on the bridge and walk across the bridge. They didn't realize that repetitive motion of people taking step after step after step, that it would actually affect the bridge itself. And so it started to create waves, and this actually turned into a giant S. Now this bridge didn't break down, but the Tacoma Narrows Bridge in Tacoma, Washington, that one was due to wind vibrations. They didn't take into account the wind. That was it's windy up there, and so they didn't take into account the wind, and so that one actually had such a large wave within the bridge itself that it actually broke down. So anyway, the point that I want to make is waves are a result of motion. Now, we're going to go in a minute and talk about what waves really are and things like that. But waves are a result of motion, okay? So we've talked about motion in terms of velocity and speed and acceleration and those kinds of things. But what happens when you have back and forth motion? Okay, so let's say that you have, I'm going to draw real quick. Let's say that you have like a little ball on a stick. And you make this ball go back and forth like this. Okay, so it's swinging back and forth like this. Okay, if you were to take some snapshots, at some point the ball would be here, and at some point the ball would be here. And so at this point, this is called equilibrium. And so this is just a basic pendulum, by the way. There's a whole bunch of math associated with this, but we're not going to get into that. But anyway, so this is called the equilibrium. This is where, over time, due to friction, it would come back to this spot right here, and it would be completely still. But the maximum distance over here, it actually stops for just a brief second, and then it goes back this way. And then it'll go from here, stop for a brief moment, and then come back this way. And so eventually it will just go back and forth and back and forth and back and forth and forth until it gets to its equilibrium. Now it does slow down eventually because of friction. But if you were to, let me redraw this. Let's say that you had a scenario like this. And you had a pendulum with, I don't know if you've ever seen those paint ones where they put a box or a bucket of paint and, they let the paint drip on a canvas. This is how some painters do it. But if you let this go back and forth like this, like we were talking about, and you're swinging it back and forth, and you were moving this canvas, say this way, it would start to look something like this. You would actually have a wave on your canvas. Now, that's a very specific circumstance, but the point is back and forth motion creates waves, okay? All right, so let's get into our essential question for today. The essential question for today is, oh, I forgot to say, this is Unit 3. Let me add a page here. This is Unit 3. Real quick, I'm going to move this page over here. I'm going to put a little nice and big, Unit 3. All right, so the essential question for today is, how do mechanical waves, because there's different types of waves, there's electromagnetic waves, and then we also have mechanical waves. How do mechanical waves transfer energy through matter? Okay, so we talked about what causes a wave, but you know as well as anybody, because we've talked about this, kinetic energy comes from motion. So if you have a back and forth motion, you have some type of energy, but what results from that? That's the question. This is what happens when you have sound, when you have light. We're talking about electromagnetic waves, light's part of those. If you're talking about mechanical waves, this is how sound happens, things moving back and forth. I mean, if you were to take just a quick little example, you can do this sitting at your chair right now. If you were to take your pencil that you're writing with or some kind of device and wave it real fast next to your ear, you will hear the actual pen waving back and forth. Now, the pen's not moving, you're moving it, so that quick back and forth motion actually causes sound waves to emanate from it. Okay, so let's move on a little bit. The next thing is, this is topic question number 1. It says, what is a wave? All right, so let's go into this. What is a wave? So a wave is a disturbance that transmits energy through matter or empty space. Now we know these to be kind of back and forth motion. That's the actual wave itself. But this is, this is the basic definition. Through matter or empty space. Okay, so now there are 2 types of waves. You have mechanical and you have electromagnetic. Okay, so let's talk about a couple of examples here. So you have water waves, are an example of mechanical waves. Water waves, like when you throw a rock in a lake. You have sound waves. And you have seismic waves. So earthquakes and things like that. Okay, now, mechanical waves, nice little definition. This is when you transmit energy through matter. That's the definition for a mechanical wave. When you transmit energy through matter. All right, electromagnetic. Couple of examples of electromagnetic waves. You've got radio waves. You've got microwaves. You've got X-rays. Okay, light also fits in here. This is where light comes in, but basic definition for this one is it's going to be when you transmit energy through matter and or empty space. All right, now moving on to the next one, topic question number 2. Okay, the question is, what is a medium? All right, so a medium, a medium is the matter through which, a mechanical wave can travel. Now, for the first half of this unit, we're really going to talk about mechanical waves the most. We're going to get into sound later on this week. Today is just basically the basics of waves, what happens, how does a wave behave, and things like that. Now, we're talking about a medium. A medium is what the wave actually travels through. So here's the question. How does sound from your headphones, if you're watching my video right now, getting to your brain so you're understanding what I'm saying? How is that happening? Okay, it does have to travel through a medium, okay? So it is going to travel through the air. It's going to go through your ears. There are bones in your ears, and that's connected to your auditory nerve, and on and on and on. Okay, so the medium is going to be, it fits into 3 categories: gas, solid, and liquid. So sound waves can travel through a gas like air. Sound waves can travel through a gas like air. You can also, water and sound waves can travel through a liquid like the ocean. This is how dolphins communicate. They have sound waves that go through the water. Water and sound waves can travel through a liquid. Like the ocean. Okay, and then the last one is going to be a solid. Seismic and sound waves can travel through a solid. Okay, now the question is, do sound waves travel fastest through solids, liquids, or gases? Now, take a second to think about this. I want you to think about it on the molecular level. You know the difference between solid, liquid, and gases, but which one would allow it to move through it faster, solid, liquid, and gas? Okay, take a second to answer. The answer is a solid. Now, the reason why it travels through it faster is because the particles are packed together. Particles are packed together. And because they're packed so closely together, sound can, they have stronger bonds between them. They're packed together, so the sound can, easily move through them. And so, anyway, so sound waves travel 14 times faster through iron than through air. This is why Native Americans used to listen for trains by putting their ears on the track. And so instead of just listening for the train, they would put their ear to the track to see if it was coming. And then if there was one coming, they could hear it they could hear it through the track long before they would hear it through the air. Okay, next topic question. This is number 3. Topic question number 3. What are the main types of mechanical waves, and how do they transfer energy? What are the main types of mechanical waves, and how do they transfer energy? Okay, so we've got 2 types of mechanical waves. So first off, we had 2 types of waves itself. We had mechanical waves and electromagnetic waves. Now we have 2 types of mechanical waves. Now, I would like to review real quick perpendicular and parallel. Parallel was when they run together like this in line with one another. This is parallel. And perpendicular is when they intersect each other at a perfect 90-degree angle. All right, so that's parallel and perpendicular. Okay, so let's talk about transverse waves. So transverse waves, the particles of a medium vibrate in a direction perpendicular, so I'm just going to draw the symbol, perpendicular to the direction that the wave moves. Okay, so for example, like a kind of a good visual for a transverse wave would be like if you're at a ballpark or a stadium and somebody does the wave in the stadium. If you actually want to look this up, the world record for the stadium wave, actually, that's really interesting. It was like 170,000 fans or something like that. So that would be something interesting for you to look up. But anyway, so it's a Guinness World Record for the stadium wave. And so that's because the reason why that's a good example of a transverse wave is because the particles, which is the people in the wave, they are moving perpendicular to the direction. So when the waves happen, people stand up and then they sit down. But yet the motion of the wave is side to side as it goes through the stadium. So anyway, so if you wanted to draw this, let's say here is a, let's see if my drawing skills here, hand, finger, 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 it's terrible. There's a hand there, and you were to take a rope, if you held it between two fingers like this, and you were to take a rope and do it like this, and you were to move it up and down. So I actually like to do this in my classroom, and I would have a giant spring, and I would have one person over here holding it, and I would have another person over here holding it. It's a very long spring, and so we actually hold it, and I move it up and down like this. Okay, and then the waves eventually will get to this other person. They move this way. Anyway, let's move on to the other type of wave. So we did transverse wave. So let's do longitudinal waves. All right, so longitudinal waves are when the particles of the medium vibrate in a direction parallel, so I'm going to use this symbol for parallel, parallel to the direction that the wave moves. Okay, so I actually like to do this one in my class too, and so I use the same spring, but the direction that I move it is different. Now before I was moving it up and down like this, and the waves eventually got to the other person. Now this time when I would do it is we would hold the spring between us. Oh, I didn't mean to erase my arms there. We would hold the spring between us like this, and I would move it this direction back and forth like this. It's still back and forth motion, also known as an oscillation. Back and forth motion are known as oscillations. But I would move it back and forth like this, back and forth, side to side like this. Now what would happen is as the wave went through the spring, it would actually bunch up, and so it would bunch up, and then it would, would bunch up again, and so you would see it bunch up.
Waves are produced as a result of vibrations and can be classified as transverse or longitudinal. Whether they are transverse or longitudinal depends upon how the particles are made to vibrate as the energy passes. Let's look at longitudinal first. This is where the particles vibrate parallel to the direction in which the wave of energy is travelling. Notice that the ends of the slinky don't ever leave the hands holding them. It's only the energy that travels. The places where the coils or particles are bunched together are called compressions. Where they are furthest apart are called rarefactions.
So when they are super bunched together, those are called compressions. And when they're furthest apart, those are called rarefactions. I think I'm spelling that right. I think there may be an E in there. Anyway, so moving on, we are on topic question number 4. What is the anatomy of a transverse wave? What is the anatomy? Okay, now notice that this question is very specific. It says transverse wave. So this is not necessarily going to be the same. I've kind of already taught you the difference between rarefaction and compression for a longitudinal wave. So we're going to talk about a transverse wave. So I'm actually going to draw one here. And so I'm going to draw a dotted line. It's right across. And so this is going to be called, some people call this the equilibrium point, equilibrium, or the origin. In your little quiz today, it's called the origin. You could also be heard to the midpoint, but this is back when we were talking about the pendulum. That was when it had that straight down, and that's where, you know, it would eventually come back to where, you know, the equilibrium point. Okay, so that's what that line is. So I'm just going to draw a basic wave here. This is not a uniform wave, so, you know, don't come for me. But anyway, so I'm going to give you the basic definition, or the basic parts of this. So the bottom part of this wave is called a trough. The top part of a wave is called a crest. Now, depending on how high the distance between the midpoint or the equilibrium point of the origin and the top of a crest, or from the midpoint to the bottom of a trough, that is called an amplitude. Now, if you're dealing with sound, if you increase the amplitude, then that means that it's going to get louder. Okay, it's going to have more energy. Okay, it is louder. So increasing the amplitude means that sound is going to get louder. Now, from the top of a trough to the top of another trough, that's called a wavelength. Now, this can be very different, okay? If you've got, you know, a very, just kind of like a really low sound, like if you were on a piano and you touched the keys that were very on the low side of a piano, then the wavelength is going to be rather long. But if you touched a key on the upper side of the piano, the really high parts, it's going to look more like this. Okay, so that's a difference in wavelength. Now, one other thing that I want to talk about is frequency. So frequency is going to be, so there's a couple of definitions that I missed here. Let me go back and give you some official definitions. The amplitude is the distance from the midpoint to the height of a crest. And so we talked about wavelength, we talked about midpoint. Okay, so let's talk about frequency for a second, and this will be our last definition for today. Frequency is the number of crests that pass a certain point in a given amount of time. And so tomorrow we're going to go more into how to calculate frequency and how to calculate wavelength. But let's take this into account. Let's talk about frequency for a second. So let's assume that the width of this paper is 1 second. Okay, let's just say that it is. Let's just imagine that it is. Okay, and so we've got 3 waves: 1 wave, 2 wave, and 3 waves. We have 3 waves that happen within this 1 second time span. So let me redo this one here. Well, that's terrible. Let's try again. Okay, so we've got 3 very different waves. Now, let's say that this is a 1 second time span across this paper, like from here to here is 1 second, from here to here is 1 second, from here to here is 1 second. The frequency is how many waves you have happen in a certain amount of time. So this one you would have, let's see, this is 1, 2, 3, 4-ish. This is it's like 1.3. This is like 25. Okay, that's a lot. Okay, so it's how many waves you've got in a given amount of time. Okay, so if you have any issues and there's any blanks that you've missed in your notes, let me know. I may have missed something. Anyway, so if you have any issues with any of this or you need some clarification, let me know. You know where to find me.